Welcome at this episode of Getting Technical. Today we are going to talk about heat and temperature, and like everything in life, too much is too much and too little is no good either. Too hot is too hot and too cold is no good either. And we are going to see that that applies very much in machining also. And if we talk about temperatures, how important are temperatures when we talk about machining processes? Well, let me quote here a friend of mine, Professor Stahl in Sweden, who says that the temperatures that develop in machining processes have the decisive effects on a lot of technical stuff. But in the end, if you add everything together, cutting temperatures affect very much also the global production economics. With other words, temperatures also affect the economical outcome of a machining process. So the impact of temperatures goes rather far. Today, we talk about expensive words, applied thermodynamics in machining processes. We talk about heat and temperature. And we are going to learn in this session that cutting speed is perhaps the most important cutting condition when it comes to the amount of heat which is generated during machining. And if we look to high-speed steel tools from a long time ago, cutting speeds were around 20 meters per minute or something like that. And if we looked into those situations, the maximum temperatures in cutting tools which were observed were around 800 degrees Celsius. With carbide tools of today, which we use with nominal cutting speeds of 200 meters per minute or even more, the maximum temperatures we observe are also around 800 degrees Celsius. So we are confronted here with the situation that today we use cutting speeds 10 times higher than we did X amounts of years ago. According to the first statement of the thing we will learn today, that would mean that 10 times more heat is generated, yet the temperatures we observe in cutting edges are roughly on the same level. How do you feel about that? What do you think about that? Put it in the comment, your thoughts on this, at first sight, a bit of a dilemma. More heat is generated and it doesn't lead to higher temperatures. What's going on here? Well, that type of things is what we are going to talk today about. Of course, again, I'm not here on my own. I have my 4 colleagues, Alesia, Olivier, Margarita and Viju. They work behind the scenes. They make all of this from a technical perspective possible. So all 5 of us, we are going to talk with you today about temperatures and heat. And let me start with the general machinability model. You know, I always use as a reference, if we look to machining, machining is a process where there are lots of different things happening, mechanical phenomena, thermal phenomena, tribological phenomena. Today we focus on the thermal things. And there are quite a lot of elements, variables, factors influencing those things. And machining is about solving this, I always say, equation. Make sure that all the variables together function as such that all the different phenomena which are taking place during machining are well in balance, are well under control, and I have a sustainable machining process, a reliable machining process, a machining process that delivers what it's supposed to deliver, a correctly finished workpiece at a certain cost in a certain time. That's why we do it. Now, to know if you solve the equation in a correct way, you know my belief. I always say that look upon this in a pragmatic way. Ask the people involved, people with some expertise in machining. They will tell you how they felt about the process, and have a look at the used cutting tools. Used cutting tools, if you know what to look for, they tell you quite a lot about what happened during a machining process. And if we look to machining, it's mechanical thinking, and that is what most of us are rather familiar with, I guess, but it's also thermal effects. During machining, material is deformed, and if you deform material, heat is generated. And if you allow heat to concentrate, it rises the temperatures there where the heat is concentrated. And that is what we are going to talk about today. What is the heat which is generated? To which extent does it lead to increased temperatures? What are the influencing elements on this? And very important, what are the consequences of this? And I'm going to focus on insight here. I'm going to focus on insight in physical phenomena. All the calculations I leave out of this presentation, because once again, in present times, we should not worry too much anymore about what I refer to as being the machining mathematics. We have today tools that makes life easy for us. We have things like Seco Suggest that do all the calculations for us. For me, it's important that we as machining experts, we have insight. We know how to give a certain interpretation to values coming out of all the calculations. And first, a very important thing I want to bring back in mind, the material we machine has a decisive effect on the amount of heat which is generated. And perhaps you remember in one of the previous sessions we talked about workpiece material properties, and we explained that there are 5 properties we have to bear in mind when we look to the machinability of a workpiece material: the hardness, the abrasiveness, the adhesiveness, the strain hardening, and the thermal conductivity. Now, when we talk about machining from a thermal perspective, and later on in a couple of slides from here, I'll explain about that heat generation. But for the time being, let's say we can consider machining as being a process where heat is generated. Machining is kind of a heat generator. And that heat shows a natural tendency to spread out, which is favorable for us machinists. The heat will spread out, and when the heat spreads out, it doesn't concentrate, it doesn't increase the temperature so much. But the question is, to which extent is it for the heat which is generated during machining possible to spread out? And in that respect, there is one property we have to bear in mind specifically here, and that's the thermal conductivity of the workpiece material. Now, thermal conductivity is a physical property that indicates to which extent a material, when you induce heat in it, when you put heat in it, is the material going to allow the heat to spread out or not? High thermal conductivity means that if you put heat in a material, the heat will spread out rather easily, meaning you don't have concentrated heat, meaning the temperatures stay rather low. When you have a material with a low thermal conductivity, the heat stays concentrated there where it is put in the material, and that concentrated heat will increase the temperature quite a lot. Now, if we compare different types of materials, and that's what you see in the graph here, and perhaps it's not so readable, I don't know, but if you look to different types of workpiece materials we kind of machine nowadays, you have the traditional steels and stuff like that, which have, let's say that thermal conductivity is somewhere on a level of let's call it 100%. And if you look to other types of material, the more problematic materials in this aspect, being the nickel-based alloys, the titanium alloys, the super alloys, that type of materials, there we see that typical thermal conductivity are on a level which is 7-8 times lower. If I say thermal conductivity in steel is 100, well, the thermal conductivity of titanium is somewhere around 15 then. That means that titanium does not transport the heat away. It lets the heat be focused, concentrated there where it isn't used, there where the ships are made. And that means that if you have low thermal conductivities, whatever heat is generated during machining, if you have low thermal conductivities of the workpiece material you machine, you'll see that the heat stays concentrated in the cutting zone and leads, logical-wise, to higher cutting temperatures. But we come back to that phenomenon. But first, the consequences. Well, the consequences of it is, and here you see a graph, and you see from right to left materials on the horizontal line ranged by low thermal conductivity to high thermal conductivity. Non-ferrous materials, what you see on the horizontal line to the left, are materials with rather high thermal conductivities. The steels, the stainless steels, the superalloys to the right have low thermal conductivity or lower thermal conductivity. That means, the black line in the diagram, that the heat which is generated during machining does not spread out to the workpiece material, the ships which are formed, but the heat has to go somewhere. So if the heat doesn't go to the workpiece, if the heat doesn't go to the ships which are formed, the heat will go to the cutting tool, and that gives me the red line, sorry. If you have more heat going into the cutting tool, the black line, that leads to the red line now, a lower tool life. There is a very clear relation between heat transfer into the cutting tool and tool life. More heat in the cutting tool, lower tool life. And more heat in the cutting tool you have if you have workpiece materials with lower thermal conductivity. So tool wear, tool life is very strongly depending on thermal conductivities of the materials which you machine. Another thermal property related to this is what is called the specific heat. Now, what is specific heat? Again, it's a physical property, and it indicates the amount of energy which is needed, the amount of heat which is needed to increase the temperature in a material by 1 degree Celsius. And some materials have a rather high specific heat, and other materials have a rather low specific heat. But most important is that the specific heat is depending also on the starting temperature. If you have a material and it has a temperature of 20 degrees Celsius and you want to increase it to 21 degrees Celsius, you need a certain amount of heat, energy. But if that same material is already on a level of 200 degrees Celsius and you want to increase it again by 1 degree Celsius, well, you see that the higher the starting temperature, what you see here on the horizontal line, it's showing the starting temperature of a material. The higher the starting temperature, the more energy, the more heat you need, the vertical line in the diagram here, to increase the temperature by 1 degree extra. And you see, and the red line peaking in the diagram is a typical line for iron. And what you see is that the amount, if you put heat in iron, the temperature increases. And the more heat you put in, the more the temperature will increase. But the higher the temperature, relatively seen, the even more heat you need to put in to increase the temperature even 1 more degree. And somewhere around 800 degrees Celsius, and by the way, it's the same 800 degrees Celsius I was talking somewhere in the beginning of this presentation. That's a coincidence. But anyway, somewhere around 800 degrees Celsius, the amount of heat which is needed to increase the temperature by 1 degree more is very high. This phenomenon is also referred to as a thermal wall. It is kind of that increasing temperatures above 800 degrees in iron is a very difficult exercise. By the way, historical, that's why it took people so long to be able to do something with iron, because the furnace you need to melt iron or to take iron out of iron ore is demanding enormously, quite a lot of energy, quite a lot of heat. A thermal wall, a thermal barrier people talk about here. But on the other hand, if you see in the diagram, you also see some lines which are rather flat. Those lines are very typical, the specific temperatures, specific heat, for stainless steels. And what you see there is that the thermal wall is kind of missing. Meaning, if you are machining and the heat, the temperature in the stainless steel is approaching 800 degrees Celsius, and you think the same things will start to happen like when you machine steel, well, it will be different. You can easily heat up stainless steel compared to steel easily with a relatively low amount of energy, heat, up to for temperatures higher up than 800 degrees Celsius. So specific heat, thermal conductivity are two properties we need to bear in mind if we talk about how the workpiece material we machine will influence thermal effects, thermal phenomena during machining. Just to give you an idea what we are talking about here, you see some materials. The red line in the bottom is an aluminium alloy. Then in the line in the middle is a traditional steel, and the line, kind of left going up very fast is a titanium alloy. Well, you see here roughly maximum temperatures we see during machining related, in relation to the cutting speed you use, which is the horizontal line. And you see here that, aluminium, the temperatures stay rather low even at very high cutting speeds. That's why high-speed machining, for instance, in aluminium is a rather easy exercise. In steel, you see that temperatures somewhere stabilize around 800-900 degrees Celsius. You know, the thermal wall which is there. And you see that in titanium alloys, where titanium with a low thermal conductivity, so the heat cannot get away out of the cutting zone, then it goes to the cutting tool, that very fast you have rather high temperatures. Different materials behave differently. Now, what exactly is going on? And here you see some filming of a machining process, filming with a temperature-sensitive camera. You see here the machining process filmed, and the colors represent different temperatures. The more the color goes to red, dark red, black, the higher the temperature. And what we already see here is that if you talk about temperatures during machining, it's quite a dynamic thing. It's a little bit like with cutting forces. People always think it's stable. You have a cutting force of X Newton and you have a temperature of 800 degrees Celsius. Well, machining makes our life a little bit more difficult than that. Cutting forces are dynamic, they change all the time, and cutting temperatures are also dynamic, they also change all the time. Now, what is going on during machining is a deformation process. So you deform workpiece material, and you deform it so much it shears off. And if you deform workpiece material, and we see that deformation takes place in machining in 3 zones. You have the primary deformation, the main one where actually the ship is formed. You have the secondary deformation zone where the ship is gliding over the rake phase, and you have the tertiary deformation zone where the clearance phase is kind of rubbing against the just machine surface. Well, in those deformation zones, heat is generated. It's kind of a heat generator. And the speed with which you deform the material, and that is influenced by the cutting speed, is the main fuel for this generator. It's a very simple thing. Higher cutting speeds, higher deformation speeds, and higher deformation speeds gives you more heat generated. Now, heat shows a natural tendency to spread out. In thermodynamics, it's called entropy. It's that thing, that physical phenomenon that makes that energy, once it's kind of generated, shows a tendency to spread out. And in case of machining, the spreading out can be into the workpiece, into the ship which is just formed, and into the cutting tool. And what you see is that as the heat spreads out, the temperature starts to increase, both in the ship and the cutting tool and the workpiece. And ideal would be that we can minimize the heat that goes into the cutting tool, because when heat goes into the cutting tool and when heat increases the temperature in the cutting tool too much, at one level the cutting material will lose the ability to cut. So we have to be very careful with that. And if too much heat goes to the workpiece and the temperature in the workpiece is increasing too much, it could well be that increased temperature gives your workpiece kind of a thermal treatment, which is not wanted. So also there we have to be very careful. And with other words, machining is a process where we say ideal is that we avoid heat in the cutting tool. Ideal is that we avoid heat in the workpiece, but the heat wants to go somewhere, then the heat needs to go to the ship. We need to put as much as possible the heat in the ships. Very often you'll find in the literature that people say 80% of the heat should go to the ship. Now, personally, I find that a little bit theoretical. I prefer just to make the general statement saying the more heat that goes in the ship, the better. Because more heat in the ship means less heat in the cutting tool and less heat in the workpiece material. So we have a machining process. Heat is generated where the material is deformed. That heat spreads out, and that leads to higher temperatures in ship, workpiece, and cutting tool. Now, there also we have to bear in mind that there is not one temperature, but there are several temperatures as the heat spreads out. For instance, if you look along the rake face, and that's what I try to show here with the diagram, from right to left, you have a certain temperature on the cutting edge, and as you move away from the cutting edge on the rake face, the temperature is increasing until it reaches a certain maximum level, and then it's decreasing again. So on a rake face, where the ship glides over, there is not one temperature, there are a range of temperatures from a certain minimum. On the cutting edge, it increases to reach somewhere a maximum, and then it goes down again. The same phenomena we see on the clearance face. As we move away from the clearance face, here from top to bottom, top is the actual cutting edge, and then along the clearance face we move away, we see that there is a certain temperature on the cutting edge. As we move downwards on the clearance face, the temperature goes up, and then somewhere it reaches a maximum, and from there on it goes down again. So temperatures in a cutting edge are different. At different places we see different temperatures. And that's interesting to observe, because if you look to a used cutting edge, what you see is that there are different wear patterns also depending on where you look. And perhaps here I'm jumping already a bit, but you know there is a very clear relation between the actual temperature the cutting material has somewhere on the rake face and the clearance face, and how the wear develops there. This explains also why we see different wear patterns on one cutting edge depending on where you look. Because we have different temperatures. And that is what this diagram shows. I think this is one of the most beautiful diagrams in machining. I have to admit also one of the least understood diagrams in machining. What you see here is horizontal different temperatures. And what you see vertical is the appearance of different types of tribological effects, different types of wear phenomena. You see from lower temperatures to higher temperatures, from left to right, that when the temperature is rather, let's say, low, You have a certain type of speed with which the wear develops. And as you start to increase temperatures, you see that adhesive wear patterns and abrasive wear patterns, and I hope you are a bit familiar with those things. We already spent at previous Getting Technical events attention to this. You can always watch it back there if you are not so familiar with these type of things. But adhesive wear increases rather rapidly when the temperature increases. Abrasive wear also, but less. Until somewhere when you reach a certain temperature, the appearance of adhesion leading to adhesive wear goes down again. It's kind of like it disappears. But at the same time, chemical wear picks up. And when temperatures are rather high, next to abrasive wear, you see that also chemical wear starts to pick up. And this diagram shows us kind of one-to-one, if you look to wear on cutting edges, let's say, I'm a little bit lying now, but anyway, for the sake of understanding here, what you see to the left, you could say, is also kind of the cutting edge. And if you move from left to right and on the horizontal line, kind of, you could say, you move away from the cutting edge. You move on the rake face, away from the cutting edge. And then you see how different wear patterns starts to develop at different places on a cutting edge, on a rake face, on a clearance face. That is very short, very briefly, how we can describe machining from a thermodynamic aspect. Machining, the deformation of material, which machining is generating heat. And that heat shows a tendency to spread out. And the amount or the level to which the heat can be spread out is depending heavily on the workpiece material, see thermal conductivity, see specific heat. And as heat can spread to the ship or to the workpiece material, less heat goes into the cutting edge. But if that is not possible, take for instance if you machine titanium materials where the ship kind of says, no heat for me, I don't take it. Yeah, the heat which is generated then goes into the cutting edge. And heat in cutting edge, heat that focuses there, that leads to certain temperatures in the cutting edge, leads to certain type of wear development. And wear development leads to certain tool life. And tool life is the bridge then to the economical thing, what Professor Stahl said in the beginning with his quote. Heat and temperature are next to technical stuff also influencing economical consequences of machining. Now, if we talk about cutting conditions, very, very briefly. First, I need to explain a bit, if you are not familiar with it, what we refer to as a temperature gradient. A temperature gradient is if you have a piece of material and part of the material is rather hot, high temperature, and another part of the material is rather cold, lower temperatures. Well, the difference in temperatures you see in different places in a material, we kind of refer then to that as there is a temperature gradient in a material. And if there is a temperature gradient in a material, that will lead to stresses. Because where the temperature is high, the material kind of wants to expand. Where the temperatures are low, the material kind of wants to contract. That means that between different places in a material, there are stresses that develop. We refer to that as thermal stresses. And thermal stresses, when they become higher than the strength of the material, will lead to cracks, thermal cracks. So 3 important things to remember from here on. Temperature gradient, differences in temperatures in one material, in one body of a material. That leads to thermal stresses, and thermal stresses, there is a risk that thermal stresses leads to thermal cracks, and thermal cracks, of course, weaken the structure of the material. Now, if we look, and I hope you recognize by now this type of photos, what you see is a cutting tool. You see the cutting edge to the right, close to the red zone. Then on top, you see the rake face. Going down, you see the clearance face. The ship is gliding over the rake face on top. And the different colors here represent different temperatures. What you see here is to the left a harder material, to the right a softer material. Different hardnesses of material means that when you deform them, it's easier to deform a softer material. Easier to deform means also less heat is generated. When less heat is generated, that leads to lower temperatures, and we see that very clearly here in the thermal photos. Softer materials, lower temperatures in cutting tools, in the cutting edges. This is one of the reasons why, for instance, in softer materials, we can use higher cutting speeds without limiting the tool life too much, because, there is so little heat generated. See the material properties that relatively seen, developing more heat by using higher cutting speeds is not really a big thing. It becomes slightly different if you look to the situation. Now I take one workpiece material and I machine the workpiece material to the left with a lower cutting speed and to the right with a higher cutting speed. And you see, first of all, that the maximum temperatures are more or less the same. And this is a bit the question I asked in the beginning also. On the one hand, I say, higher cutting speeds means more heat. But on the other hand, here you see higher and lower cutting speeds, but it seems that higher cutting speeds, more heat is generated, but it doesn't lead to higher maximum temperatures. Still an interesting question. I hope to find some interesting thoughts on this in the comments after this presentation. We see roughly the same temperatures for the moment. Just to be nasty, I'm not going to answer my own question. I leave it up to you to think a little bit on this. What's going on here? But anyway, what is important for me here is not to focus on the maximum temperature, it's the same anyway, but it's to focus on the temperature gradient. And what we see here is there is a certain temperature gradient, and now I'm doing kind of just again for the sake of understanding, the distance, the surface over which this temperature gradient can be divided, leading to thermal stresses somehow, and I hope there are no metallurgists or physicists in the group here, because otherwise I could receive some very nasty comments, I guess, on what I'm going to say now. But one could say is if you have a certain temperature gradient and you can divide that temperature gradient over a bigger surface, what you see with lower cutting speeds is that it will lead to lower thermal stresses. And lower thermal stresses means that there is lower risk for thermal cracks. And if there are lower risks for thermal cracks, it means that statistically seen, the risk that the tool breaks, prematurely breaks, due to thermal overload is lower. Lower cutting speeds means that the impact from the thermodynamic effects on a cutting edge are lower than when you use higher cutting speeds. If you look to feeds, lower feeds to the left, higher feeds to the right, here you see the same thing, but even more than in cutting speeds. You see to the left lower feeds that the temperature gradient is to be handled by a rather small surface, while with higher feeds the same temperature gradient can be spread out over a bigger surface, leading to lower thermal stresses, leading to lower risk for thermal cracks. The risk that you kill a cutting edge by premature breakage due to too high thermal stresses is lower at higher feeds and lower feeds. This is the background why we always say if you machine materials which from a thermodynamical perspective are a bit tricky. Think on titanium alloys, superalloys, because their thermal conductivity is low, that it's better to work with higher feeds. Because the risk that you break cutting edges due to too high thermal stresses is lower then. Geometries play an important role. Here you see the example of a T-land geometry. The picture here is the more positive a cutting tool is, the smoother it cuts. And smooth cutting means that the heat which develops is lower, and if the heat which develops is lower, the cutting temperatures are also lower. You see here an example of 3 geometries, 0 degrees, 5 degrees, and 10 degrees, positive then. T-land geometry, and you see a very clear difference between, I take here the example of 850 degrees Celsius. Imagine that would be a limit for you. Well, 850 degrees Celsius, you always, even at low cutting speeds, will be higher if you have a 0 degrees cutting edge T-land geometry. If you have more positive tools, you can increase your cutting speeds and still stay below that, in this example, critical border of 850 degrees Celsius. Geometries are very important in this respect also. And that leads to the final question, from a thermal perspective, what's the best way to machine a material? And you see here 3 examples. 3 times, the material is stainless steel. You have here 3 combinations of cutting conditions. All 3 gives you the same metal removal rate, with other words, kind of the same productivity of the machining process. And on top, that is realized with a low cutting speed combined with a high feed. And then in the bottom, it's a high cutting speed combined with a low feed, and in the middle it's kind of an in the middle situation. And what you see here is that if you cut the time in cut, when the time in cut is increasing, and as the time in cut is increasing, also the wear is increasing. Here we see kind of 2 phenomena at the same time, that the heat leads to different pictures of temperatures. You see in the top, the heat is more and more concentrating as time goes by in the cutting edge, but at this moment in time does not reach a critical level, while in the bottom you see that the temperature starts to go up and up and up, and after a while even is becoming problematic. So you have here 1 cutting tool, 1 application, workpiece material type application, 3 combinations of cutting conditions. And what you see is that in the top, you can continue to cut with the cutting tool with no worries. You don't have a dangerous situation yet. In the bottom, you went now in a situation where perhaps it's better to change the cutting edge. And you see, one could say from left to right, you have kind of tool life limitations. In the bottom, you already reach end of tool life. You need to replace the cutting edge before you continue. While on top, you still can continue to use this cutting edge, no worries. So heat and temperature are kind of a relation maker between tool life, tool costs, and metal removal rate. Bear in mind, and what you see here is a simulation, bear in mind that all of this, so far I have been using photos, but that these type of things are very much dynamic. In time, things are changing. Temperatures are going up and down, up and down. Now, this temperature thing also leads to a situation where other phenomena start to take place. Here I take the example of side flow effects on a cutting edge, which are very much depending on the heat which is generated, the temperatures in the cutting zone. Well, these side flow effects will influence the surface roughness of the machine surface. So heat and temperature also influence the quality of the machine surface. Now, if we look to milling applications, here, I already said, heat and temperature are dynamic. It's going up and down in time. It's depending on the place where you look for certain temperatures. It's depending on workpiece materials. Now, if you look to a milling application, that notion of it's dynamic goes one level higher. Because if you look to a cutting edge cutting, in case of a milling application, a cutting edge, as the milling cutter is turning around, part of the time a cutting edge is not cutting, part of the time a cutting edge is cutting. So the temperatures in a cutting edge, even on a bigger scale, are going up and down all the time. And if you look to different types of application, and I compare here slot milling, where the milling cutter is full in cut, and side milling, where the definition says less than 30% of a milling cutter is in cut, we see here different situations, because if you have slot milling, the milling cutter full in cut, the temperature that develops in a cutting edge will reach rather fast, rather high levels. While in side milling, the same phenomena goes on, but much slower, as the part where a cutting edge is cutting, with other words, where it's heating up, is rather limited. And that means slot milling, you have to worry about temperatures that are too high. But you know, side milling, you also have to worry about temperatures that stay too low. Because if the temperature in a cutting edge is too low, the cutting edge, the structure of the cutting material is rather fragile, and a cutting edge rather breaks easily. You need to be with your temperatures in what I try to visualize here in the diagram, in the yellow zone, where the temperature is not too high and the temperature is not too low. But I'm not going to explain too much on this, because this is now the subject of the next event we plan for, because here we talk about compensation principles. A last word on cooling systems, because it comes in one chapter. If you talk about heat which is generated, if you talk to temperatures which are developed due to that heat, of course we also talk about cooling. We need to talk about cooling. I'm not going to talk about the chemical side here, you know, additions and stuff people add to cooling systems, because that's a whole subject on its own. I'm going to focus here just on the physical aspects, the cooling system we use. I start with no cooling, the so-called dry machining. Dry machining is machining where I do not apply cooling. And we saw that in such a case, heat develops, heat spreads out, heat leads to different types of temperatures. Today we use mostly, or today and by historical, we use mostly what is referred to as emulsion cooling. Emulsion cooling is, you know, to do effective cooling, you should be able to put the cooling where the heat is generated, on the cutting edge, where the material actually is deformed, but that's physically impossible. The pressure between a ship and a cutting tool is so incredibly high that it's impossible to bring the cooling in between the ship and the tool to there where the heat is generated, and so the cooling can take the heat and evacuate. Most cooling systems we use today work indirectly. We kind of submerge the whole thing under a very big volume, abundantly applied cooling, and the heat through the ship is evacuated in the cooling, and in doing so we lower temperatures. This is the traditional emulsion cooling. A further development on this is the so-called MQL cooling. MQL is a different physical approach to the same thing. How can the heat which is in the ship evacuated away out of the ship, so more heat can go into the ship, so more heat leaves the cutting zone. MQL, we count on a different physical perspective thing. You know, it's like when you jump in a swimming pool in summertime, you cool down because the water is cold. That's what we do with emulsion cooling. When you come out of a swimming pool, you have a thin layer of water on your skin, and that evaporates in the sun, and that evaporation process takes heat away from your skin. So this MQL system also works. The most modern system we use today is so-called HPDC cooling. It's highly pressurized directed cooling. It's yet a different principle of cooling which is developed in the aerospace industry and which is, from an effectiveness perspective, the best system, because here we truly can approach a situation that the cooling enters truly there where the heat is generated. What we count on is so-called kinematic pressure. It's if the speed with which the coolant is applied, if that is increased, you have a totally different system, and that leads to a much better evacuation of heat out of the cutting zone. It's called HPDC cooling, highly pressurized directed cooling systems. Mostly known under all kinds of commercial names. In case of Seco, we refer to it as the jet-eye cooling. But all of that is just how it's called commercially. If you apply cooling, however, and I let you enjoy this movie, you know, if I'm out in workshops, you find all kinds of adventures. And I can't help myself taking photos and films. What you see here is a cooling system which could be discussed concerning efficiency. What I try to say here is use cooling. There's one the discussion, should I use cooling? Yes, no. But anyway, if you decide to use cooling, do it correctly. Yeah? I mean, do it there where the cooling is needed. If you go for emulsion cooling, it should be abundant fluid on the cooling process. It should be well in time. Cooling should start before machining starts and should stop after machining stops. All that kind of practical stuff, you know. If you do it well. Machining thermodynamics, what did we say? We said heat is generated in the shear zones, mainly the primary shear zone. That heat that shows a tendency to spreads out in the cutting edge, in the workpiece and in the ship, and increases the temperatures there. I use on purpose plural, temperatures, more than one. There is not a temperature in the cutting tool. The ship does not have a temperature. There is a gradient. There is a multitude of temperatures. Now, in traditional machining, it's not the maximum temperature that is potentially problematic. It's the gradient we have to worry about, because the gradient temperatures leads to thermal stresses that could potentially lead to thermal cracks. Thermal cracks that would lead to premature breakage of cutting edges and would limit the tool life and all the other risk that comes with a broken tool, an unexpected breaking tool. Workpiece material is a variable here. Think on thermal conductivity, specific heat is what you have to worry about. The cutting speed is the major generator for heat. And the feed also generates more or less heat. But cutting speed and feed, how they lead to different gradients, it's different. Cutting speed you should keep on the low side if you think you are in a problematic situation. In the same problematic situation, you should look for the higher feeds. So the secret to have efficient machining from a thermodynamic perspective, problematic applications, problematic workpieces, is to think in combinations of slower cutting speeds and higher feeds. Tool wear is strongly depending on this type of phenomena. And see it a little bit on a bigger scale also. What you see here is a simulation of what would happen with a tool, a milling cutter in this case, and if the heat goes up and material properties change, you could end up with a crash of a milling cutter, which is of course not what you want. And even more, you know, because if you crash a milling cutter, people always think, or I should say, if you crash a cutting tool in general, people always think in terms of, oh, I lost my tool and I need to buy a new tool and so on. Some people are aware of, yeah, but what about my workpiece? Hopefully I didn't lose my workpiece, but also there, bear in mind that the consequences of a crash are not only mechanical, but could also be thermodynamic, because during a crash, temperature, the heat which is generated and the temperatures to which it leads to different types of situations. So especially in titanium type materials, superalloy type material, after a crash, it's perhaps needed to check the workpiece not only from a mechanical perspective, but also from a thermal perspective, if you didn't make by any chance some thermal treatment, which was or which is unwanted. And with that, I am roughly where I wanted to be. This was a big subject for a rather limited time. I hope I didn't make too big jumps here and there. Again, this presentation, if you want to have a copy of it, of course you can have a copy. Just let me know and we make sure you have a copy of this. If you have further requests for more information, if you have questions, don't hesitate, put them in comments and yeah, we answer all your questions, all your comments, yeah, as good as possible. Just let us check here if we have some questions that, because we have some time left, that we can take care of today. I have here a question: do our current materials have better heat dissipation? Yeah, first of all, when we talk about heat dissipation or heat conductivity, it's not about better or worse. It's about higher thermal conductivity or lower thermal conductivity. Most of what we refer to today as the modern workpiece materials, the stainless steels, the duplex materials, the superalloys, the titanium materials have lower thermal conductivity. And I hope after this presentation that should answer your question, what the consequences are. Lower thermal conductivity, more heat goes into the cutting tool. That leads to higher temperatures, not so extremely, but to much more, how to say, temperature gradients which are on a higher level, and you will have to take care of that. Reduce your cutting speeds, increase your feeds. Then there is a next question. Antonio is asking, how much does the holder influence in the tool performance? How should I answer that? Let me say, if the cutting edge support, if the tool holder is in good condition, there is no influence. If, however, your tool holder is in bad condition, does not give the needed support to the cutting edge, then the impact is very high. It's a bit of a binary answer. I know, a bit of a 1 or 0 answer. Cutting tools, the holding tools, the tool holders, the milling cutters needs to be in good condition, and then everything is fine. The moment they are not in good condition due to inaccuracies, bad quality, surface cracks, spare parts in no good condition, you'll see a very big impact on your tool life. The third question from Kiran: can cutting oil coolant help us to reduce the temperature during machining? Yes, yes. To which extent is discussable, but it reduces the temperature. When it's well applied, remember what I said, when it's well applied, yes, it reduces the temperatures. Very clearly, and so far I was very briefly, I just talked about impact of cooling on cutting tools. Of course, cooling also is going to have an impact on your workpiece, the workpiece temperature, the surface roughness, the temperature of your machine tool, and so on. Then there is a fourth question from Shardil. Can I comment on the cutting zone in drilling of composite material? Yes, but not here. If okay, I'll come back to that later on in comments, because this will take more than just 2 minutes to answer. And I see there are so many more questions. Shardil, I'll come back to your question later on. The next question, which is better, higher edge hone or land on cutting edge, especially from the point of heat generation due to the geometry factor. We talked about 2 sessions ago. Sharper cutting edges generate less heat. Very, very simple. So from a heat generation perspective, I would say the sharper the cutting edge, the better. However, there is a consequence to sharper cutting edges, that is that they are, from a mechanical perspective, more fragile. And that's the balance you need to find here. I would say it's a balance, and that's why we have so many geometries nowadays, because there are so many applications. Sharpness is good for tool life from a thermal perspective. Strength is good for tool life from a mechanical perspective. To which level you combine sharpness and strength, and that's what we do with T-land geometries and cutting-edge geometries, that's depending on the actual application you have at hand. I think that's the best I can answer this question. The next question from Panka. How can we get reference of material properties that withstand with thermal stress? I'm sorry, Panka, but you will have to clarify this a little bit more in comments, and because I don't really understand what your actual question is. Can you clarify a little bit more in comments, and I answer the question later on then? The 7th question, how effective is HPDC in a milling cutter considering the centrifugal forces involved due to the cutter rotation? Yeah, the big discussion ongoing for today in the tooling world, because to make HPDC cooling effective, the distance between the cooling outlet and the actual cutting edge is crucial. Let me start by that, because if the distance is too big, as the cooling is spreading out once it leaves the nozzle, you lose effectiveness. So it must be close enough, but when it's too close, it's not working either. You know, it's like a flame. If you have a flame here and you keep your finger there, you don't feel anything. And if you approach the flame, it's getting hotter and hotter and hotter. But when you pass the flame and when your finger is in the flame, you don't feel heat anymore. And with HPDC, it's a bit of the same phenomenon. If you are too far, it's not effective, the cooling effect. If you are too close, it's also not effective. You need to be more or less at the correct distance. And in case of static or stationary tools, turning tools, it's rather easy to fix that from a tooling technology perspective. In case of a milling cutter, it's not so easy, and people are designing people are still struggling with that. If we manage from a tool design perspective to handle this, HPDC in milling is as effective as in turning. But today we still struggle with design issues. In case of rotating tools applying HPDC type of cooling. And next question from Anthony. What is a special grade of insert for a material of cast stainless? Yeah, that's a question I would, yeah. It's too general to give you here one answer. I would say have a look at the different types of advisory things we have available on our website and so on. Describe there your application and a little bit more than just the material is cast stainless steel. and you will be advised for carbide grade, geometries, and cutting material and cutting conditions. Sorry. That's yeah. I could yeah. No, I'm not going to give you here any designation because it's too much depending on the actual application you have. Let's see. What do we have more? Somebody is saying, oh yeah, and that's the last question because I see it's 5 o'clock already again here. Chemical wear is influenced by temperature, obviously, but adhesive and abrasive wear also. Yes, because you know if, let me take the example of abrasion, rubbing, friction, kind of, if you want. If you have a harder surface, your cutting material will be less sensitive for wear due to friction, due to abrasion. But if the temperature increases, the hardness of the material is going down. The material is softening, and if you have a softer surface, it's more sensitive for friction. More material will be rubbed away. So very clearly, all wear phenomena, being adhesion, abrasion, chemical, even fatigue wear, is influenced by the temperature in the contact zones, in the contact surfaces where the cutting tool and the workpiece meet each other. And here, if I want to keep the time right, I need to stop. If there are more questions, please put them back in the comments. I'll have a look and answer as many as possible afterwards. That brings me to the end of this one. Thermodynamics. Machining is the formation of material. Where material is deformed, heat is generated. Heat shows a tendency to spread out in case of a machining application. It spreads out in the cutting edge, in the workpiece material, in the ship. Too much heat that spreads out in a cutting tool I do not like because it leads to rather high temperature gradients. And high temperature gradients gives me always the risk that thermal cracks appear, and thermal cracks weaken cutting edges. Leads to premature breakage, leads to crashing of a cutting tool, leads to destroyed workpieces, standstill of a machine, and so on. I don't want too much heat going into the workpiece material either, because there it could change the structure of the workpiece material. It could be that unintentionally you do kind of thermal treatment of the surface. And in a big number of cases, that's not allowed. So I want to limit heat that goes into the workpiece. No heat in the tool, no heat in the workpiece, then I need to put the heat in the ships. That's what I'm after. The whole one definition of machining could be, how can I make that maximum of the heat which is generated during machining is put in the ships, because the ships goes away, and all the ships that go away takes heat with them, and the more heat that is evacuated through the ship means lesser heat in the tool and the workpiece material, which was my aim from the beginning. Next time I'm going to take this temperature thing again, and we are going to extend it into a general principle in machining called compensation techniques. And if you master compensation techniques in machining, that's a big step forward to reliable, to sustainable machining processes. But that's for next time. I hope this time was interesting. I hope you learned some interesting stuff that makes you think a bit. I'm looking forward to see comments and questions in the comments. I will answer as many as possible there. If you want to have a copy of the presentation, once again, leave me your information and we make sure you have one. Thank you very much.